Well, thank you. An honor and a privilege. Great to see so many old friends and so many new ones. So I'm not going to talk about ice cores today. I'm going to take you through sea level rise, work that we've been doing. Those of us who do big ice sheets, broadly, we want the history of climate. We want will they fall in the ocean. And if we can sneak it in, we want erosion and landscapes and fun stuff. But I'm going to do the sea level rise story here. If there's any questions, just let me know. We'll see what we can do about it. Okay? Why should you care? This is something Peter Clark put together in a review we did a few years ago. What's up here is history, various times in the past. And along the top is the CO2 level at some interval in history. And along the side is the sea level that accorded with that. Today is at 0, a higher sea level is there. Now, if you do the absolute stupidest thing, which is you take the modern CO2, you run it over to the equivalent temperature from the linear interpolation, and you ask where 10% of the world's population is, I think it's fair to say that this is reason enough to be studying ice sheets and sea level. Okay, now be very clear, this is not a projection, it's not a projection, but daggone it, that's a pretty good reason to look, because that's the modern CO2. And you know, the answer, which is we really might blow off of the side of this plot over here. And that starts getting interesting. Okay, so this is 6 meters of sea level rise. No one has never ever come up with sort of what is a plausible worst case scenario, but you know, it's conceivable that someone could think of something that was notably more than this. And I showed the 6 meters of sea level, including Washington, because people get a kick out of that for some reason. But be that as it may, it's a you know, Greenland is a little more than this, and West Antarctica is half of this, and East Antarctica is a whole lot more than this. If that arrived fairly rapidly, this is a map of the Galveston 1900 storm surge, and the very peak up there is 6 meters. So you know that if that arrived very rapidly, it would certainly be a big deal. But we sort of don't expect it to arrive quite that rapidly, thank goodness. So I have spoken to some economists. You can't say economists say, but at least some of the economists, if you ask them, so should we be worried about sea level rise? Published papers, no big deal. Says, come on. A, it's not going to be very big, and it's not going to rise very fast. And of course, we're economically efficient people, and so you know how this works. Is it that if you know, so Rob has got his beach house, and he's an economically efficient person, and he sees the sea coming, so he quits maintaining his beach house. And when the sea finally takes it, it wasn't worth anything anyway. And there's this beautiful view, but of course I own the house behind his. And when he loses his view, I get it, and so there's no economic loss at all. The view is still there. And so who cares about sea level rise? And you can find, if you look really hard, you can find 100-year loss projections for the entire United States coast that are less than the losses in Hurricane Katrina in 2005. Without blaming Hurricane Katrina on sea level. But basically what you do is you invested a little bit in avoiding climate change. You invest a lot in the economy. Your grandchildren are incredibly wealthy, and they can build whatever walls they need, or they can buy me out and get your view back. And so this is what we do. So at any rate, there's sea level rise in a nutshell. Sea level is rising, but they sort of look at something like this. This is the satellite data of sea level rise. Down here, this is 1992 over on the left, and that's right up almost to the present on the right. And this is only, you know, it's 3.1 millimeters a year. If you read the wrong blogs, they got really excited about that. That was a La Nina, that's an El Nino, and you get back to where you were. But at any rate, sea level rise, 3.1 millimeters a year. It's only, you know, about that much a decade, and it's only about that much a century. Don't worry about it. Okay. But let's look at it just a little more carefully. So as you may possibly remember, the Ipcc has sort of looked at this. And in particular, I'm going to talk about ice sheets and sea level both here. But in 2001, the Ipcc looked at sea level rise, and they said, you know, there are really big uncertainties here. But they said, well, you know, the ocean is going to go up because it's getting warmer and the water's expanding, and the ocean's going to go up because the mountain glaciers are melting. But we don't think that the big ice sheets will change their flow any. And when it gets warmer, it'll snow more on top of Antarctica. And so our best estimate is the sea level rise from thermal expansion and mountain glaciers will partially be offset by the ice sheets. Ice sheets are our friends. Next 100 years, don't worry about them. 2007, I actually helped a tiny bit on this. I helped a little more on this one. And we said, oops, the ice sheets are shrinking. And they're shrinking in part because they have changed their flow, which wasn't in this picture in 2001. And so we're not sure what to tell you. So we did what the San Francisco 49ers would call punting. We backed up and kicked it, and we said the models used to date do not include the effect of changes in ice sheet flow because a basis in published literature is lacking. Therefore, we cannot provide a best estimate or an upper bound for sea level rise. So yes, we punted. Okay. For what it's worth, you will find, though, that there are analyses floating around. We quantified what we could, and that led to numbers. Sea level rise of, you know, so much in the next 100 years. And you will find people that are actually using those numbers, discussing those numbers, working from those numbers, perhaps forgetting that that excludes future rapid dynamical changes in ice flow. So there's been a little misunderstanding of people pulling numbers out of this table without reading the heading, for what it's worth. And that may possibly contribute to some of the lack of concern about sea level rise. Okay. Now, since we punted, I'll walk this through. The Ipcc 2001 estimate for sea level rise from 2000 to 2100 is this little blue wedgie right here with the arrows on it. This is a collection of everything I've been able to find since where somebody tried to address this in a way that would provide guidance until we get fully diagnosed, properly run projective models of the future, which we don't have. And so hiding in here are estimates of sea level rise based on scalings against temperature. Hiding in here are estimates of sea level rise based on what could happen. There are estimates based on expert elicitations. There are estimates based on what has happened in the past. There's a couple of models hiding in there. But basically what you'll see is that this is the Ipcc range, excluding future rapid dynamical changes in ice flow, and most of what's on here is above that. And so this is sort of a probability density function of the Ipcc quantified range, and above it there is maybe more like a probability density function of what could happen. If you ask me to defend this in an Italian court, I would be ducking and running really fast and be very clear. This is not a prediction. This is not a projection. We don't know. We don't have the full understanding, and I'm going to show you why here in just a minute. And then the other piece, so people are saying, well, it'll be slow and small. Well, maybe it'll be bigger and maybe faster. But it is at least worth asking whether, in a world where we don't mitigate and we just adapt, whether we really will respond in an efficient manner. And so I can tell you, I'm not going to blame Katrina on sea level rise, but I can tell you that I spent over a decade teaching that it was coming. And basically every geoscience prof I know who taught introductory geology taught that it was coming. And we taught it using materials that were often prepared by the government for the government with government funding. Everyone who was paying attention knew without any shadow of a doubt that sea level is rising, New Orleans is sinking, the protective delta is eroding, the storms might be getting stronger. And of course all of those have influences on optimal levee engineering. So it is at least worth asking, if we are in a world where there is economically efficient response to knowledge that absolutely unequivocally was in the public sphere for decades, whether this is in any possible way could have happened. Okay, so for what it's worth, Okay, so we can then go into this question, will the sea level rise be slow, small, and expected? And a very good approximation, this is a question, should we fund ice dynamicists more? Because this really is a question, what will the big ice sheets do with their flow? Because if we walk through everything, okay, you make the ocean warmer and it expands. And the number is in round sort of 0.7 of a meter per degree C warming. That varies a little bit if you're putting the heat into colder water or warmer water. There's a curve in this thermal expansivity, but basically that's the right thing. The whole warming from the glacial maximum to today is only something like 2.7 Celsius with an uncertainty of a couple tenths. That's from noble gases and ice cores. And so, you know, that's only a couple of meters of thermal expansion since the Ice Age. This can't be something that's really fast and really big. Mountain glaciers, huge amount of interest in them. They're very fascinating. They're good indicators. They matter to local water supplies. They do matter to sea level. But they're gone before you get to 0.5 meter. There just isn't that much ice on the mountains to make a big difference. Groundwater, there's a lot of uncertainty, but most people think that the sort of renewable, exchangeable resource is pretty small, that we start running out of easily pumped groundwater before we can make a huge difference in the ocean. And so really, the 7 meters in Greenland and the sort of 60 meters in Antarctica are what determines whether sea level rise will be slow, small, and expected. Okay? What the ice sheets are doing now, year 1960 is on your left, year 2010 is over on your right. This magenta line at 0 is neither change nor loss. Above it is the ice is shrinking to raise sea level. So up is raising sea level, and down is lowering sea level. And here is sort of a coastal temperature curve for Greenland, and this is what Greenland was doing. On here are all sorts of things. So this is repeat altimetry. Go over with an aircraft or go over with a satellite with a laser or a radar, measure surface elevation, measure its change. On here are estimates of snowfall and estimates of mass outflow. On here are weighing the ice sheets using the Grace gravity. Also on here are assessments where people pull it out of their ear or wherever they pull these things out of that include everything. And the basic picture, it was sort of warm and it got cold and it warmed up and the ice sheet was shrinking and then it got stable and it's shrinking. Okay, Greenland, pretty easy. Warmer, melts. It also flows faster, as we'll see, but Greenland's actually pretty easy. Yes, there's probably more snowfall in the middle as it warms, but the melting on the side wins more. And so it's pretty straightforward for Greenland. I'll show you the history later, but it's the same story. As we turn up temperature too much, Greenland gets in trouble. Antarctica, way more uncertainty. And I will tell you that there is some likelihood of taking all of these data points and moving them up or down a little bit, because there's some history of isostatic response which is included in here, which is moderately uncertain. But this recent trend that Antarctica is shifting towards mass loss probably is pretty good, and that is almost entirely an ice flow effect, not a melting on top effect. So the ice sheets look like they're contributing mass to the ocean. They're shifting in that direction, and they're doing so at least in part because their flow has changed. Okay. So let me do the physics of glaciers for you. We could sing this later. But do the physics of glaciers. If you want rho GH alpha and integrate through thickness and the longitudinal deviatoric stress and the stress tensor and so on, we can do that later. We've got that all. But the truth is, the physics of glaciers are fairly straightforward, and they're fairly easy to do at a broad level, so we can talk about the details that matter. So if you make a pile, it tends to spread under its own weight. That's the physics of glaciers. If the pile is really strong, it doesn't spread too fast. Most buildings like this one are actually not bulging out on the walls, but you know that some of the Gothic cathedrals had problems with spreading under their own weight, and the roof caves in and the side bulges out unless you have a flying buttress. Okay? So strength is one of the things as to how fast your pile spreads. The other things, basically, if you pour water to make a pile, it spreads out really easily. If you pour pancake batter, it spreads out more slowly. If you pour pancake batter on a waffle iron, it doesn't spread as easily as if it's on a greased griddle. So a lubricated bed spreads more easily. And if you pour your pancake batter and hold it in with your spatula, it doesn't spread as easily as if you get the spatula out of the way. If you're doing a building and you're holding in the walls with your flying buttress, that opposes spreading compared to no flying buttress. Okay? That's basically the physics. All right, an ice sheet, a 2-mile thick, 1 continent wide pile of old snow turned to ice. It's sitting there spreading under its own weight. We used to get mailings from these people who had discovered that it snows in Greenland and Antarctica. And they were very worried about this because the snow is going to build up and build up and build up, and the world is going to roll over. And they the only way to save the world was to haul the Ross Ice Shelf to the Sahara Desert with the aircraft carriers and water the Sahara and save the world. Okay, so in point of fact, the snow piles on top and the thing spreads under its own weight and it makes icebergs, or else it melts at the edge and it comes close to being a balance. If you snow more, the pile gets bigger. If you melt more, the pile gets smaller. If you spread faster, it will get to where it can melt or can make icebergs, and it will shrink the pile. And the snow comes out of the ocean, so if you grow the pile, the ocean goes down, and you shrink the pile, the ocean goes up. And the one we're really going to worry about is this question of, if you make it spread faster, you are raising sea level. Okay? And we're going to walk through 2 pieces. The strength of it, it's ice. I cut thin sections of ice. There's a sea-axis fabric history that's fascinating. The ice can change a little bit. It doesn't change very fast. Ice is mostly ice. So the strength is more or less fixed. And so the things we really need to worry about for the future of the ice sheets are just 2. One is basal lubrication. The other is flying buttresses. So I'll walk you through the 2 of these. Changes in basal lubrication are probably going to be less important. Changes in flying buttresses are probably going to be the thing we have to understand. Okay. So first of all, changes in lubrication. If you follow the public literature on ice sheets, this is the story that's gotten the press. There are these gymongous lakes that form on the surface of the ice sheet. The flow comes down, it hits bumps in the bed, it makes little rumples, it melts, it puddles, and it makes lakes that are a few kilometers across and tens of meters deep in the middle. And then these lakes break through. And so this is Sarah Das, Woods Hole, who did her PhD with us. And it's not this lake, but it's a lake like this one. They set up a grid around this lake, and they went out in their boat, and they measured the depth of the lake. And then one night, the lake drained in about an hour. It was doing twice Niagara Falls into a crack in the ice sheet that went to the bed. And there's a crack, and here's the crack. And it was really spectacular. And the whole ice sheet sort of lunches up about 1/2 meter, and it lurches sideways, and it goes faster. And in a week, it slows down again. And integrated over a year, it didn't mean much. And this got huge amount of press. If you missed it, it was absolutely spectacular. But be that as it may, it probably doesn't make the ice sheet fall off of Greenland and flood the coasts. And the reason is that there's big bumps under here. Greenland is gnarly bedrock. And so here's a air above ice above rock. And what you have is where the ice has to flow over these highs in the bed, you get these local reversals to get the lakes drain through to the bottom. That makes it more lubricated, but it just can't fall off because the bumps are in the way. There is an interesting piece to this, which is we know, because we drilled an ice core in here, that it's -9 and it's frozen to the bed. And we know these are thawed at the bed, and when it thaws, it can slide. And even if it's gnarly bedrock, that still makes it go a good bit faster. And if you make it warmer up here, and then you say, how long will it take that heat to go through the ice to the bed? It's sort of 10,000 years. That's the advective conductive time scale, is about 10,000. If you have a lake and you break through in a crevasse, how long does it take to get to the bed? About 10 minutes. And so the most important thing with these lakes is the question of whether these hollows are going to fill with lakes that break through to the bed, that thaw the bed, that let it slide faster. But it's still centuries or millennia to kill Greenland. It's not decades. It can't fall off in the ocean as far as we know, because we can't figure out how the ice can get off of this gnarly bedrock that's sitting underneath it. So Greenland's great stories. It's fascinating physics. It's volcanoes upside down, basically. That's a magma chamber going through a crack. But ultimately, probably this is not the biggest deal. But it's still worth remembering that Greenland, when it gets warmer, tends to melt. So this is a historical plot. We went back through time and said at various times in the past, sort of what's the North Atlantic temperature look like relative to today? How much had Greenland contributed to sea level rise? Today is in here. When it was colder, Greenland was, this is colder. This is lower sea level because Greenland had grown. And when it was warmer, Greenland is smaller and sea level is higher because the ice is in the ocean. And this number is between 2 and 7 Celsius above pre-industrial conditions. If sustained, is probably enough to remove Greenland. So, but think centuries or millennia, we don't think decades. So, the really interesting issue is the flying buttresses. This is what's going on at the coast. So remember the picture. A Gothic cathedral without a flying buttress, the roof tends to sag in, the walls tend to bulge out, and it falls down. An ice sheet spreads under its own weight. It comes down to the coast. It does not immediately break off icebergs. It flows over the ocean. It may run aground on a high spot in the bed, or it's in a bay and it's scraping past the rocky sides. Friction here, friction with the sides. That slows down the spreading. That means the ice sheet is bigger than it otherwise would be. It's minus 50 up here. You warm it to minus 45, big whoop. It's at the melting point here. It's close to the melting point here. You raise it a little bit, and it's a different story. So there's the one we're going to look at, is what happens down here. And many of you have seen these pictures. This is now becoming old history. This is January 31st, 2002. But this is a really important thing. We are over here looking at the Larsen B Ice Shelf, right there on the peninsula, sticking up towards South America. Here's the peninsula on the left with the glaciers just dripping off of it. Ocean is in black out here. Scale bar, that's 20K. So these are bigger than aircraft carriers. And this thing in here is the Flying Buttress. That's the Larsen B Ice Shelf. And to the best of our knowledge, it formed 10,000 years ago, sort of as the ice sheet shrank back from the Ice Age. And it sat there for 10,000 years. It's got friction with these rocks up here. It's got friction with rocks down here. And this funny-looking stuff on top of it is meltwater sitting in crevasses. Now, when the meltwater breaks through in Greenland, the ice sheet doesn't fall off on the ocean because there's lots of bumpy rock underneath providing friction. When the meltwater breaks through in the Larsen B, nothing underneath but water. No friction. Friction's on the sides. So what happens, let me first make the labels go away, and then I'll make the ice shelf go away. This is January 31st to March 7th. So in a few weeks, this ice shelf went away. This stuff in here, the blue slushy, you'd probably run your kayak through. It's little tiny broken up bits of ice. These are icebergs, but this thing is gone, and it's gone in a few weeks. When that went away, this one is going about 8 times faster than it did before. So this doesn't raise sea level, but loss of the friction on the sides lets this one go faster, and that does raise sea level. So basic picture, this happened. It's real. Fortunately, it's the Antarctic Peninsula, which isn't terribly big. And so if I blow this up a little bit, this one goes away. There's still a piece down here, but this one goes away, but there's only a little tiny bit of ice behind it. The interesting question is, all these other green things are flying buttresses, and there's a lot more ice behind them. So what are they going to do? And that's what we need to look at, because right now these things have been marching down the peninsula falling apart, but these big ones down here haven't fallen apart yet. Okay. Now there was a very recent paper, Helmer et al. 2012, that ran some models into the future and said, you know, if we turn up CO2, at some point hot water gets under here. And I'll show you what hot water does if it gets under. It's not an entirely pretty thing. But we're going to actually focus on a different one here for a little bit and see what we do. Okay? It is worth asking the question, you know that this went away and these went faster. But how do we know if this one or some of these other went away that would go faster? And I'll show you a couple pieces of evidence on that. This is one of them. My colleague Sridhar Nandakrishnan went right here, and he put in a bunch of GPS, and he monitored the motion of the glacier on really high time resolution. And what happens is here is the speed of the glacier day to night to day to night. This is the tide cycle is a daily tide in the Ross Sea. When the tide goes up, there's more water pushing back and the ice slows down. When the tide goes down, the ice speeds up. The tide goes up, the ice slows down, and it works beautifully. And you can actually sort of see a little bit of the spring-neap cycle in here running across. So right at the grounding line where the ice starts to float, it is responding immediately and directly to the tide, and its speed is varying sort of twofold. 80 kilometers upstream takes a few hours. So you'll notice this slant is just a few hours, 80 kilometers away is responding to the tide. So if a 1 meter tide is forcing the velocity 80 kilometers away in a few hours, you can be pretty darn sure that when you lose friction down at the end, that the ice farther up will notice and it will respond. So take it as confident that if we lose these flying buttresses, it's going to matter as you go in. Now that's also shown by the results from Greenland. So here we are looking in along this yellow arrow at Jakobshavn. This is the view along the arrow. Rock on your right, rock on your left. The great ice sheet is at the end. We're looking up a long, deep fjord here, about 6 kilometers across. Up to there, way up in here, this is actually broken up icebergs and sea ice sitting on top of ocean water. If you get in your helicopter and you fly to about there and you look out the window, you'll see a seal. So in point of fact, there is ocean water under there. But if you keep flying past a seal, you come up through this and you get to this 100-meter high cliff, which is sitting on 800 meters or so below sea level. And this is not floating on your left, and this is this broken up stuff on the right. Okay? Now, if we go back to this picture and we look down from our helicopter or our satellite along the smiley face, what we see is this. So the seal was down here on your left, rock at the top, rock at the bottom. The ice sheet is flowing in from your right along the arrow. This is this broken up stuff. In 1992, the ice was out here, and all of this was a flying buttress. It was an ice shelf. At that time, this was maybe the fastest glacier on the planet. It then thinned, and the ice shelf completely broke out, and it is retreated the front back to here as one with no ice shelf. And in doing this, the flow velocity doubled. It's almost tripled, actually. And so what you have is loss of the flying buttress, which had friction with the rock on the sides, has allowed this flow velocity to about double. Now, what killed it, we're pretty confident at this. When the thing was happy, this is a temperature against depth profile out at the front of the ice where you could actually get in and make measurements in the ocean. So this is temperature in the ocean from the surface going down, and it's in blue because it was pretty cold. When the ice shelf went away and the ice doubled its velocity, the temperature profile out there was this red one. And the difference between those two is about 1 degree. So 1 degree up, thinned the ice shelf, then the ice shelf fell off entirely, then the flow velocity doubled and more. Okay? So that's sort of the issue that we're interested in at this point. This is just a plot, a correlation, so this is not models or anything. This is how much the temperature is above the in situ melting point down along the bottom of the ice shelf. So, and this is 1 degree above melting, this is 2 degrees above melting. And on this side is how fast the ice shelf is melting for an existing ice shelf today. So this is just a plot of various ice shelves and how fast they melt as a function of ocean temperature. And the number is sort of 10 meters per year per degree. So a little bit of ocean temperature makes a lot of melt. Ice shelves are typically a few years to a few centuries or even a millennium long in terms of flow. So the time ice takes to go through an ice shelf is years or decades or something. And if you warmed them by a degree and the melt goes up by 10 meters a year, most ice shelves are not thick enough to persist. They go away. So 1 degree is a huge deal for an ice shelf. Okay. There's probably hysteresis in these as well. We wrote some stuff on calving laws, and that increases with the stretching rate. And there's a bunch of data that tend to support that this happened, and it really did happen in a couple places. As you warm the water and thin the ice shelf, at some point, rather than the ice shelf getting thinner and thinner and thinner, it just breaks off. And so the drag from the ice shelf gets smaller and smaller, and then boom, it jumps to a new state. And it's pretty clear that that's what happens. And then you've got to get the ice shelf back, but it's a hard thing. So there's probably hysteresis in this system that makes it a little bit scarier, for what it's worth. So we've looked up here. I've showed you a little bit down here. What we're going to do, everything that's in color in here could make icebergs if it wanted to. If you get rid of the ice in the colored regions and just get into this gray, it's like Greenland. It would be Greenland, once we get out of the fjords, it'd be a big lump sitting on a continent, and it just sits there and melts. But anything in color can make icebergs, and so those are the areas that we're interested in. And in fact, we're going to focus in this area because that's the one that has the greatest ability to make icebergs. Zoom in a little bit, and we're going to look through this area. I'll show you a couple of things from here and a couple of things from here and here. Because there's this interesting question. If I'm supposing that this ice could go away, has it ever done so in the past? And the truth is, this drives me crazy, we don't know. We don't absolutely have a smoking gun on this. But I can tell you a couple of things. One is if you go all the way in here, there are very indications of young diatoms under the ice, open water diatoms, not windblown. So it's pretty clear that sometime in the last 700,000 years, the ice went away. People have been mapping relatedness of bryozoans on the continental shelf, and the ones over here and the ones over here and the ones over here are really closely related. And the ones in between that you'd have to go around, so if we even go back here, these and these and these are really closely related. And it doesn't make sense unless you get the ice out of the way. So the bryo people say, well, maybe the ice went away. And there's a bunch of other sort of, yeah, that's probably right, but we're not certain, that tend to say that the ice sheet did go away, probably during the previous interglacial, probably during 5E. Maybe the most likely argument on this is just a far-field indicator. If you go to a lot of islands and you look on these islands, you find corals from 130,000 years ago that are well above the beach, including islands which are not cranking up really rapidly for tectonic reasons. And when people look at the pattern of how high those corals were, and do the full solution for the isostatic adjustment and the self-gravitation of the ice sheets and so on, various studies are now pointing to the same answer, which is 130,000 years ago, sea level was maybe 7, maybe 8 meters higher than today, and that it had a contribution from both poles that was big. You can't just do this from Greenland because the pattern is wrong. You actually need to do this. A lot of this is this self-gravitation. That the ocean, an ice sheet is so big that it actually pulls the ocean towards it a little bit. And if the ice sheet melts, it raises the ocean, but then this relaxes because the ice sheet's smaller. And because of that, you can't get the pattern of observed things around all the high stands by taking all the ice out of one pole. You have to take it out of both poles. And so this says Antarctica put a lot of water in the ocean at 130,000 years ago. Some models do this as well. It is not too hard to make a model that goes from an Ice Age ice sheet to a modern ice sheet to that sort of ice sheet under plausible forcings. Okay. So we'll go back here, and I'm going to take you to probably the worst place. So we're going to zoom in on that little area right there, Thwaites Glacier. This is a plot of flow velocity in that previous square. Black is really screaming fast. This one is getting all the attention recently, but it's sort of like Jakobshavn. It's sitting in a bedrock trough. We don't think it can do immense amount of discharge because it's this narrow, constrained by bedrock. There's ice at the surface, but down below there's this deep, narrow trough. This one, you'll notice that the fast velocities are sort of a funnel extending off into the inland of West Antarctica. It doesn't have a lot of sides to slow it down. So that one's the one we're going to especially look at, is Thwaites Glacier. If we zoom in on that little block right there, this is a satellite picture of it. The ice is flowing down from your right. This is ice that is not floating. It goes to float about there. This is the Flying Buttress, sort of broken up looking beast. But there's still probably some friction from that. And so let's zoom in on this a little bit. That previous picture, I should have squared it. That previous picture was about right here. This is the bed topography with all of the ice removed. And right now, the ice starts to float right here, and it's sort of up against this, which is probably a volcano, and it's up against these highs. So there's sort of a bedrock high right here with lots of pinning points. And then it goes into this trough. And these numbers, this is 2,000 meters below sea level. The ice is, most of a mile above sea level, but it goes way the heck below sea level as well. This could dump an insane quantity of icebergs if you actually got a calving front back in there. You don't camp right under El Capitan because you're afraid of granite falling on you. If you put a calving front back in there, it'd be higher than that. And ice is not granite. So, so this is the thing we're really worried about. The ice sits right here, but if it retreats, it goes into a deep hole. Okay? So now let me tell you about what that bump is doing. We've been interested in this for a long time, and what I'm going to show you, geological evidence, geophysical evidence, glaciological modeling all agree that the ice sits on a high spot. And when it moves off of that high spot, it does not do so slowly and gradually, it jumps. There's a threshold behavior in this. And I'll show it to you. Like I said, I'll show you a couple pieces of this version. But because it's sitting on this high spot, it would not retreat gradually back here. Based on history and physics, it would retreat rapidly. And I'll try to see if this will work. So first of all, this is a model. We did this with 3 different models in 3 different ways. I'm going to force this one with sea level rise, but you could do it with temperature. And so what we're going to do here is say if sea level is rising, I'm going to eventually float this ice, which is flowing from left to right, and I'm not going to let it retreat past here. But on a perfectly smooth bed, that is what sea level rise or melting at the edge would do to the ice. It would thin and it would float, and it's not very exciting. Now, if we do the same thing here, except I put in a little topography, what would happen is that nothing, whoop, jumps to the bump. Now notice, almost nothing happening. It's sitting here. This is where it is today. It's sitting here, it's sitting here, it's sitting here, it's sitting here. Watch. Okay. All the different classes of models that we've got do the same thing. I can run them next to each other just so you see it once more. If the world were perfectly smooth, it is not terribly exciting. It will retreat gradually, but in a rough world, this is where it is today. Forcing gets almost no response, forcing gets almost no response, forcing gets a huge response. Okay? This is our best understanding of what it does. Is that happened in the past? Okay, this is a picture of the seafloor. Ice flowed along these yellow arrows. This is sort of flutings on the bottom of the ice. There are no deposits across here indicating a still stand. And then there's this humongous sediment wedge here. The ice sat there for 1,000 years putting up a big pile, and then it jumped out of sight with no pauses. We're fairly confident that a 1-year pause leaves a recognizable deposit, but there's no pauses evident. So the geology is saying what we've been seeing. It sits, woo. Okay? And that's where it's sitting today, is right at the edge here. This one's a little deeper. It might possibly hang up there. And then essentially the next stop is the Transantarctic Mountains. And that's about 3 meters of sea level as best as we can tell. Okay? This would be a profile coming in along a flow line there, and it's on this bump, and there's maybe another bump or so, but this is getting pretty deep. Remember, this is 2,000 meters below sea level. So if you once lose a bump or two back here, we're not sure what could stabilize it in that giant funnel spreading out inland. So what do we do with this, right? We are not anywhere close to making a prediction on this. It might sit there for centuries or millennia. It might survive the interglacial altogether. We're not sure it went away in the previous one. We don't really have this nailed in any fundamental way, but we can think of a disaster scenario that kills us in a big hurry on this and puts 3 meters of sea level rise into the ocean. And rather than talking centuries to millennia, you start talking centuries to decades. And would I pound on the table about any of that? No. We do not have the physics of a mile-high cliff in anybody's calving model at this point. Okay? So let me do this. What do you do with this? You know, you go down to Congress and they say, what do we do? I don't know. It's your job. Okay? But let me do this. A couple of you have seen this, but suppose that you actually were a Bay Area commuter and you drove a car. Okay? What do you expect? You get in the car, and the most probable outcome is you sit in traffic for a while. You turn on a radio, and it's the Captain and Tennille singing Muskrat Love. Okay? Right? What's the best thing that can happen to you? There's no traffic, and it's the Beach Boys Festival. But let's be honest, that's not very likely. What's the other side? Well, there's lots of traffic, and they're testing the emergency broadcast system. But what's possible is you're sitting there in traffic, and a drunk driver runs over you, and you're dead. What we expect as commuters is way over on the good end of what's possible. And what do we do about it? We have cars with airbags and crumple zones and anti-lock brakes and seat belts, and we have child seats, and we support mothers against drunk driving, and we do all kinds of things. We put a real fraction of our transportation into something that we do not expect to happen because it's a big deal. Now, I've spent a lot of my career looking at things that may not happen. We may not shut down the North Atlantic. We may not have a giant jump in things. We may not collapse the West Antarctic ice sheet. But I have yet to see any plausible story in which cranking up CO2 turns Earth into Eden. And I have seen some stories where we get pretty fast sea level rise, or we get pretty fast climate change, or we get pretty fast ecological change. And this really, I think, is an apt analogy to the commuter, that we really do what we expect is on the good end. And there's a lot more room out here. This is still the most likely one. The ice sheet sits there for a while. We're okay. But I can tell you for what it's worth that my personal experience is I have spent a lot of my life having this argument so that we have both sides. And I'm just not entirely convinced that that argument represents both sides. And so I really go with that, right? Sea level rise almost unavoidable. If you see the published numbers, they lack the ice sheet contributions until the AR5 comes out. We'll see. The economic costs are usually made to be small, but that sort of assumes that it's not going to be very fast. We'll see it coming and we'll act efficiently. History raises questions about whether we'll act efficiently, and our current understanding includes the possibility of nasty things from West Antarctica. And we're working to cut that off or else strengthen it, whichever comes out. But right now, our current understanding includes the possibility of nasty things from Antarctica. For those of us doing the research, man, this is fun. You can't imagine. But for the policymakers, that plot of the curves of the commuter is probably the best I can do right now. So I want to thank you so much for inviting me. It is truly a pleasure to see you and see what you're doing, and I'll happily take any questions.